What's up, guys? I'm James Purser, and I am joined by Grace Southwick and Karloot Hernandez, who you will hear from very shortly. We are the Gapplebees.
For our first metal, aluminum, it has a face-centered cubic structure with a lattice and unit cell. It has a closed pack structure of ABC form. For our second metal, titanium, it has a hexagonal closed pack structure and its lattice and unit cell. Its closed pack structure is in AVA form. For our semiconductor A, gallium, has a face orthorhombic structure with its lattice and unit cell. There is an atom shared among the 8 corners of this box, and face centering means there are additional atoms centered of the faces of the box. The face-centered orthorhombic structure has atoms at the corners and centers of faces, leading to a unique packing arrangement. For our semiconductor B, phosphorus, it has a lattice and unit cell, which is a triclinic structure that can vary in terms of atom positions, and there is no specific arrangement.
Alright, opening up with our face-centered cubic metal, aluminum. Since it is FCC, it has a coordination number of 12 nearest neighbor atoms, 4 on each face and 4 in each unit cell surrounding it. To find its atomic packing factor, you multiply the number of atoms and the volume of each atom and divide it by the volume of the unit cell. After substituting, you get 4 times 4/3 pi r cubed divided by 4r over rad 2 all cubed. That denominator is our A value. When simplifying, you get pi times rad 2 over 6, which gets you 0.74, and multiplying that by 100 gets you 74%, which is the amount of space used by atoms in the unit cell. Finally, our theoretical density. Rho equals the mass of the unit cell over the volume of the unit cell. Our mass is found by doing 2 times the mass of aluminum, being 26.982 grams per mole, over Avogadro's number, and the volume is the same as earlier using the radius of aluminum instead. After substituting and simplifying, you find the theoretical density of aluminum to be 2.70 grams per centimeters cubed. Now, titanium is a hexagonal close packed which also has 12 nearest neighbors. The equation for the atomic packing factor of titanium remains the same, but instead has 6 atoms per unit cell. After substituting differing numbers for A and C and simplifying, you also get an APF of 74%, leaving 26% empty space wasted. Now, our denominator for the theoretical density equation is the same as the previous, and our mass equation is the same as the previous slide. This gives us a rho value of 4.50 grams per centimeter cubed.
For this project, we're going to look at the linear and planar densities of our metals and semiconductors. To do this, we need to understand directions and planes when given to us in Miller indices. First, we're going to look at the direction 1, 2, 0. When we look at the Miller indices, we associate the first number with the letter A, the second with B, and the third with C. However, we want to show this direction within our 1A by 1B by 1C box, so we want to divide each number by 2 to give us 1/2, 1, 0. So this direction is 1/2 unit in the A direction, 1/2 in the B, and 0 in the C, as shown by the red arrow. The family of directions to the right shows all of the directions that are equivalent to 1, 2, 0. Next, we're going to look at the plane 1, 1, 1. This is the plane that connects 1A, 1B, and 1C, shown by the shaded triangle in our picture on this cubic structure. Again, the family of planes represents all planes that you can make that are equivalent to plane 1, 1, 1. Next, we'll apply these concepts to calculate the linear and planar densities of our materials. We'll start with the linear density of aluminum. To find linear density, we need to find the number of atoms along the line and divide by the length of the line. Aluminum has a face-centered cubic structure, so our lattice constant is the same for A, B, and C. The lattice constant is the numerical value for our indices. Aluminum's is 0.405 nanometers. We can use this with the Pythagorean theorem to find the length of our line is 0.453 nanometers. Next, we look at our line and see that it passes through the center of only one atom, so the number of atoms is 1. Now we plug that into our equation and find that the linear density of aluminum is about 2.2 atoms per nanometer. Now let's look at titanium. The linear density formula doesn't change, but because the structure of titanium is hexagonal close packed, we have to take a slightly different approach to find the length of L. The bottom plane of one unit cell for titanium is a parallelogram, with equal sides A and B. Titanium has a lattice constant for A and B of 0.295 nanometers. We can look at this parallelogram as two separate triangles where the line we are concerned with passes through the center of one opposite side, which we can see depicted by the red arrow in the center of our slide. We can use this again with the Pythagorean theorem to find the length of our line to be 0.225 nanometers. The line only passes through the center of one atom, so when we plug our numbers into our linear density formula, we get that the linear density of titanium along the 120 direction is about 4.44 atoms per nanometer. Next, we'll look at planar densities. Planar density is the number of atoms in the plane divided by the area of the plane. Aluminum again has an FCC structure, so we can see that the plane is an equilateral triangle. When we look at this plane from above, we see that each point of our triangle occupies 1/6 of an atom, while the atoms on each side are equal to 1/2 of a whole atom. We have 3 vertices and 3 sides, so when we add each portion together, we find that the plane occupies 2 atoms total. Next, if we look at the area of the plane, we see again the equilateral triangle with side lengths of radical 2a, which we set equal to d. We also know that a equals 4r based on our structure, so d is equal to 4 times radical 2 times r. We know that the area of an equilateral triangle is equal to radical 3 divided by 4 times d squared, and if we plug all of our numbers in, we get the area of this plane to be 8 times radical 3 times r squared. Now if we apply what we found to calculate planar density, we get 2 atoms divided by our area, and that comes out to be about 10.37 atoms per nanometer. For titanium, our process looks a little bit different because of its structure. For each unit cell in HTP structures, instead of a cube, we have a parallelepiped where A equals B but does not equal C. So the lattice constant for this example are A equals B equals 0.295 nanometers and C equals 0.468 nanometers. Now, if we try to imagine our plane in this case, we get a triangle. I've drawn this triangle on the picture to the top left, but in one of its equivalent directions for simplicity. The triangle, however, is isosceles and not equilateral, so we have to find the different sides independently. To start with the shortest side, we can use the formula for the diagonal of a parallelogram to find the length. By the properties of this structure, we know the wider angle to be 120 degrees. If we plug this into the equation shown for the length of the diagonal, we get the shorter side, side P, to be 0.511 nanometers. Next, to find the length of the other two sides, we see that the length is just the diagonal of the rectangle created by sides B and C. So using the Pythagorean theorem, we find the side Q of the triangle to be 0.553 nanometers. Now that we have the side lengths, we have to find the height so that we can use this area of a triangle formula. We do this by using the Pythagorean theorem and plug our values in to get the area of the triangle to be 0.125 nanometers. If we visualize, we see that there are 3 atoms at the point of our triangle and 1 in the center of one side. Because a triangle's angles sum up to be 180 degrees, we can conclude that the 3 vertices occupy half of an atom. This, in combination with the 1/2 of an atom on the side of the triangle, gives us 1 atom occupied by the plane. Now if we divide our area, we get the planar density to be about 8 atoms per nanometer squared.
Now let's analyze the linear density of atoms for our semiconductor A, gallium. We would divide the number of atoms by length, as Gray said, which we have calculated to be 5 atoms on the 120 direction, by the length using Pythagorean's theorem and lattice constants of the orthorhombic structure. We will get about 1.61 atoms to the nanometer when calculated. To find the linear density of atoms in semiconductor B, phosphorus, we would have to count the number of atoms, which is 2 atoms in the 120 direction, and multiply it by 1/8. This will give us a total of 1/4 atoms, which would then be used by using the formula number of atoms over length to find the linear density, which we calculated using Pythagorean's theorems and the lattice constants to 0.157 atoms to the nanometer. Now let's look at our planar density of atoms in semiconductor A. Given that we have a 111 Miller indices, we could calculate the number of atoms in the planar density knowing that there is 5 atoms per unit cell. However, there are 1.75 atoms in the Miller indices unit cell. When we calculate this using Pythagorean's theorem, it comes out to be 1.75 atoms to the nanometer. Now let's look at the planar density of atoms in semiconductor B, phosphorus. The number of atoms along the 111 plane is 3 over 8 atoms, as there are only 3 atoms in the Miller indices plane. When we calculate this using lattice constants and Pythagorean's theorem for the area, it comes out to be 0.236 atoms per nanometer. These are the sources we used. Thank you so much for watching this video and have a great day.